What we want to look at now is algorithmic aspects of how to find a maximum matching. So the situation we are looking at bipartite graph. The basic thing on which the algorithm depends on is what we proved right at the beginning. Namely, you start with also given a matching. So the algorithm should either get me an augmenting path. It should either get me an M augmenting path. In case I have an M augmenting path, I can get a matching that has one edge more than the number of edges in M. Then I replace capital M by that new matching that has one more edge. Try to find if that matching has an augmenting path. And keep doing that. Obviously, this has to end somewhere because number of vertices is finite, etc., etc. In case you don't have an augmenting path, then the matching is maximum. But it should be able to, the algorithm should be able to certify. So you need a certificate from the algorithm saying that what the matching that has been found is actually a maximum matching. Equivalently, the algorithm will actually construct a cover. It will construct a cover, vertex cover that has as many edges, that has as many vertices as the number of edges in the matching. This will completely settle the question because number of basic thing on which this entire theory depends on is the duality statement, namely if Q is a vertex cover, then this inequality is true for any matching and any cover. Is that clear? It's a very strong inequality. And what we are saying is that the maximum of this is minimum of that. Is it clear? I mean, it's like this on the real line. There are people who are approaching that point from the left and there are people approaching that point from the right. Whether you do it, whether you ask people running this way on the left and going right, or running the other way, going left, you will get to the same point where the equality holds. That matching will be maximum matching and that cover will be a minimum cover. Is that clear? So this is quite a strong statement. It's a very strong statement. Procedural part, what the algorithm tries to do is something like this. So I'm given to start with some edges that are in the matching and some edges that are not in the matching. Some of these are in the matching, some that are not in the matching. I first try to see if every vertex in X is saturated. If every vertex in X is saturated, then that matching clearly is a maximum matching. Is that clear? There is nothing to prove in that case. You cannot do anything better than that. If every vertex there is a saturated vertex, that matching cannot really be. That's like saying this is a set of boys and that is a set of girls, and every boy has been found has been paired with a girl. Then it obviously cannot do it. I mean, this is of course bias towards X, so some girls may remain unmarried. But then we can interchange the thing to say that X is a set of girls, all right. Okay, and some boys will remain unmarried, etc. Okay, so let U be the set of X is M unsaturated. So the augmenting path that we want to start, it must recall the definition of augmenting path. Augmenting path is a path that starts with, this is not in the matching, the backward arc in the matching, forward not in the matching, backward in the matching, again forward in the matching, backward not in the matching, etc., etc. Finally, if I get to a vertex in Y, which has the property that that vertex is unsaturated, then the yellows can be replaced by the whites, and therefore you get a matching. Those 3 yellows can be replaced by 4 whites, and to get a matching that has one more edge than what we started with. Okay? So as soon as you will find a vertex on this alternating path in Y with the property that that vertex is unsaturated, the algorithm will stop there and you revise this matching to get a new matching, etc., etc. So entire thing now is to make a systematization of this idea. Label all the vertices I have no time to go through an actual example. I think what you should do is consult a book, okay, to actually see how you run an algorithm even on a moderately small, moderately large graph. Something like that has 10 vertices on each side, okay. Try to do that. Try running the algorithm actually. So for example, those 2 vertices are saturated. This is scan each labeled vertex and look at its neighbors. Yeah, for example, that is that has been labeled star, okay. So a forward arc not in the matching. This of course is unsaturated, therefore there cannot be an edge which is in the matching on that, that is why I labeled it, okay. So if this has a label X, this has a label star, and if this vertex actually was X, this is Y. Y gets labeled X. So Y gets a second label. Is that clear? Y gets a second name. So that name Y is there, but in bracket you write X. Why do you write X? This is just to say that that augmenting path is coming from X. The alternating path is coming from X. This is a record. This is for record purpose. That you approach Y from X. If Y is such a vertex, It may be the case that this vertex y can also be labeled by something else. Doesn't really matter. Is that clear? Once you, it is possible that there is an edge coming like that, and if this is z, I could have labeled this by z. Doesn't matter. I don't care. Once I have labeled it by x, I keep it. So don't keep erasing the labels. Okay. Matching is fixed for this entire thing. Then scan newly labeled vertices in Y. If see, the fixed rule here is backward arcs in the matching, forward arcs not in the matching. Is that clear? I mean, thumb rule. Forward not in the matching, backward in the matching. I mean, that is this is a guiding principle in this entire running of this algorithm. All the time when you move backward, backward movement means from y to x to y not in the matching, y to x in the matching. So then some new vertices will get labeled in X. Some are already labeled, some newer vertices will get labeled. I will use those newly labeled vertices to move forward. For forward arc, forward arcs not in the matching, backward arcs in the matching. Is that clear? So I keep doing this. Then scan newly labeled if because I am going forward, then W gets labeled Z. So this is sort of keeping a track of this entire thing. And suppose you begin with x1, then y1 is to be called x1, then x2, therefore this fellow is to be called y1, then it is y2, it should be called x2, then this is x3, in bracket you write y2, then this is y3 but in bracket you write x3, this is x4 but in bracket you write y3, etc. Keep doing this as much as, the moment we stop when we meet a vertex in Y that gets labeled vertex, let's call it T newly, but T is unsaturated. Yeah, like in here. This is unsaturated. The moment I get an unsaturated vertex in Y labeled, I have found an augmenting path. I should be happy. Okay, because then I know how to improve that matching to a better matching, etc., etc. If I don't succeed in that, keep labeling, keep doing this as much as you can. Is that clear? Keep doing this until you find a vertex in Y which is newly labeled and is unsaturated. Main thing is this is unsaturated. If this also happens to be saturated, then what do? I use that backward arc to, this is saturated means it is on some yellow, therefore I'll go back there, try to see if that has been labeled. If it is already labeled, then there is nothing that I can do. You don't put two labels on the same vertex, is that clear? This is the main thing for this algorithm. You don't erase any label, no erasing of labels. So the definition of breakthrough. Unsaturated. See what that means is you begin with unsaturated and end with unsaturated. Therefore, you have found an augmenting path. Why are these labels really necessary? These labels are just to tell you, this is a backtracking idea, just to tell you how Y4, where did I get Y4 from? Y4 came from X4, X4 came from Y3, Y3 came from Y3 came from X3, X3 came from Y2, Y2 came from X2, X2 came from Y1, Y1 came from X1. Therefore, that is okay. So that is the idea. Yeah.
What if it stops at some X only? It doesn't. What if it doesn't go to the?
No, that's possible. I quite agree with you. I mean, we're not finished. Okay, it is possible that such a thing, this is a happy situation. I mean, let's call it happy or whatever situation. Okay, such a thing may not happen. No matter how much I try, I may not get a vertex in Y, newly vertex in Y which gets labeled and is unsaturated. Then you don't get a breakthrough. Okay. In fact, we are going to call it a non-breakthrough. Okay. So in case of non-breakthrough, we should be able to say that the matching is a maximum matching. Okay. And that's it. So no further improvement is possible. We just close this chapter in that case. Is that clear? So that's, then we can get a matching using the augmenting path. So this is sort of an easy thing, that's clear. I mean, now let's answer our friend's more difficult question, okay. The more difficult question is, as she correctly says, what if I may work very hard, but in spite of that I really cannot get any new labels. This whole thing has sort of a confounded picture. You cannot really get anything better than that. So non-breakthrough is a negation of breakthrough. It's just a negation of breakthrough. This algorithm, by the way, I didn't tell you what this is. There are many names to this. One can call it labeling algorithm. So now we have a definition of non-breakthrough. So we should say what non-breakthrough amounts to. No unsaturated vertex in Y gets labeled. So all the vertices in Y that received label, they are all saturated. And no further labeling is possible. This labeling is a sort of dynamic procedure. You label things in, you begin with, you label things in X, then that gets labels in Y, then labels in X, labels in Y, labels in X, etc. Is that clear? So it's a two-way track. Let S be the set of all those X's in X. X is labeled. T So in case of non-breakthrough, I really want to make a strong claim. What is the claim that we want to make? We want to make the claim that the matching M is a maximum matching. In fact, I will show you a cover, a vertex cover, whose size is equal to the size of the matching, and therefore that will completely prove that the matching is a maximum matching. So that's the theorem. Let non-breakthrough occur let ST be defined as before. As before means on those lines. Okay? Then M is a maximum matching. Several claims in fact. Let Q be equal to X minus S disjoint union T. Then Q is a vertex cover. Size of M is equal to size of Q. M is a maximum matching. And Q is a minimum cover. Duality is a very strong theory in this area of combinatorics. Very strong ideas. So see, there are lots of claims that are being made here simultaneously. Proof. One by one. Every vertex in T is saturated. That is clear. Why is that? Because if T does have unsaturated vertex, then that is what we mean by breakthrough. That is exactly the definition of breakthrough. Okay? Since we have a non-breakthrough, Where did, these are all saturated, that is fine. So take one such vertex here. Let's call this Y. It gets labeled. It gets labeled by what? It gets labeled by something which comes from S, of course. I mean, because there are labels in S already. But the thing is, it is in the matching. Therefore, let look at X itself. This is X. X is saturated. The set that I have called U there is actually part of S. It's a small portion of S. Okay? X is saturated, therefore X was not in U. X of course was not in U. Why did I put X in S? Because using some backward arc, which is this backward arcs in the matching. Therefore X must have received the label Y. X must have received the label Y. Okay? Okay. This X really cannot be in X minus S. That's clear. If it was in, then it remains, then it cannot remain unlabeled. It must be labeled by Y and it would get into S, which is contradiction. So that the X cannot really be in X minus S. What about the vertices in X minus S? Consider. What about such a vertex? Is it saturated or not saturated? It is saturated. Only the vertices in U are unsaturated here. In X minus S, let then W cannot be in T. If W was in T, then Z could have been labeled backward arc in the matching. I could have labeled Z by W. Okay? I mean, maybe it should be written WZ instead of ZW. Okay? No, ZW, no, that's fine. W is here. So if W, Z could be labeled W. Contradiction. So, thus edges of M either match T into S actually S minus U, because U consists of unsaturated vertices. Or but not both. Hence, size of M is equal to size of X minus S plus size of T. Edges in the matching that are on T actually are getting into S. They don't go to that side. If they did go to that side, you would have labeled it. Backward arc in the matching, you could have labeled that, then that vertex would be pushed into S. But you did not. The fact that you did not push that vertex into S means that matching actually is going into S only. Whereas these are also saturated, but they get into Y minus T. We now claim that Q equal to X minus S disjoint union T is a vertex cover. Okay, so it must cover every edge. If the edge has 1 foot in X minus S, you are okay. So only edges that possibly may not get covered are the ones that go from S to Y minus T. Those are the only ones. Suppose then X must belong to S and Y must belong to X is in S means X is labeled. Why did I, after all, I could have used this XY as a forward arc. But X is labeled. How could that happen? Well, the only way that could happen is by having that edge xy in the matching. In the matching. If it is not in the matching, then it's a forward arc that I can use. I can label y by x. Okay. But this is not true. You see, all the things all the vertices in S, the vertices in U got labeled first. They were unsaturated anyway. Therefore, then X is saturated, implies X is not in U. So X got labeled Not in the first round. It got labeled in the 10th round or 20th round or whatever. How did it get labeled? It must have gotten labeled by using label of some vertex in T, using the backward arc. That means it's as good as saying that there are two edges on X which are in the matching. How could that happen? X is labeled implies that the backward arc this contradiction shows that we have no such edge. Hence, Q is a cover. Also the size of Q, which is equal to size of X minus S plus the size of T, which is same as size of M. Therefore, M is a maximum matching and Q is a minimum cover. Therefore, we are through. The labeling algorithm that I just described is a part of a much bigger scheme. This is called, we will be looking at it subsequently after a few lectures, and this is called the network flow theory. Network flow theory. There is a flow theorem of which the labeling algorithm is a very special case. Labeling algorithm is a special case of the flow theorem. That is what is called the Ford-Fulkerson algorithm for the network flows, and this is a special case. So network is a much more general model than the bipartite graph that we are looking at. So it's a far much bigger object, and we'll look at the things that time. So the networks come with capacities and the idea of a flow, etc. So we'll look at those somewhat later. So this is a much more special case. Labeling algorithm will terminate after a few steps because the number of vertices here is finite. Every time you will be adding one more edge in the matching, etc. Therefore, it is clear. In case of non-breakthrough, you will stop at that point. Therefore, this algorithm works. Having seen all this, there is a variant of this question. In fact, there are several variants, but there are two important variants. One of which is the idea of the following kind. So now take quite a simple model where X consists of vertices x1, x2 up to xn. Y consists of vertices we want to assume that you have a complete bipartite graph here. If you have a complete bipartite graph, that means every possible edge is there. There are as many as n square edges with you. You can certainly find a matching. You can find a perfect matching. In fact, every perfect matching in this situation actually corresponds to a permutation. It actually corresponds to a permutation, and conversely. What has happened is, on every edge, there is a weight assignment. W is a function, so So this is a complete with a function w which tells you the mapping from the edge set to non-negative real numbers. Weight of the edge xi yj is wij. See, it is like this. I mean, let's put it this way. There are four men and 4 women. Then there are 4 factorial ways of pairing them. Is that clear? There are as many as 4 factorial permutations that you have. For every permutation, if ith man is paired with jth woman, this is sort of a measure of happiness that you have. Is that clear? What you want to have is have measure of happiness for the matching given let M be a perfect matching there exists a permutation alpha in the symmetric group such that xi is paired to y alpha I. Then weight of M is just the sum of weights of these. So if I have 4 men and 4 women, there are as many as 4 factorial perfect matchings that I will get. For each perfect matching, I can find this weight by adding those weights of all those edges. Among them, I want to find that perfect matching whose weight is the largest possible. So this is sort of to be taken as a measure of happiness. So you want to make the total as large as possible among all the perfect matchings. So this is what is called the weighted bipartite graph matching problem. This problem, because of its importance, has attracted a lot of attention. This is one way of handling by putting weights. Other idea is, book by West discusses it, but we don't have in the syllabus, so I won't get into this. Other idea is what is called stable matchings. The stable matchings are interesting discrete objects. So treat these as boys and treat those as girls. Each boy has a ranking on the girls. Is this clear what I am saying? Each boy has a preference list with him. So he ranks girl number 1 at the top, then girl number 2, girl number 3 in that manner. This is true for every boy. He has a different, each boy has a different list in his hand. The same thing to make it symmetric problem. Each girl also has a ranking on the set of n boys. You want to make a pairing in such a way that somehow you find an idea of happiness, stability in this. You want to make a perfect matching in such a way that some kind of stability is achieved. This is what is called stable matching problem. Okay? That problem is more discrete than this, than the weighted bipartite graph matching problem. Okay? Yeah, in fact, there are only 2 ways in which you sort of measure up people. I mean, this is a philosophical idea. If I have 10 people standing there with me, one way is ranking them. I like this person the highest and then the next one, etc. Other way is I put weight on each person's head. Is that clear? I mean, this person is worth 1,000 rupees or 400 rupees or whatever. Is that clear? So we are sort of following the weighted idea here. And those are the only two sensible ways of in which mathematics can come into play. Unfortunately, the mathematics that goes on with this problem can be solved, but is not as easy as the case of unweighted situation. Why does one do weighted bipartite graph matching problem? Because it's a lot more general, therefore more applicability, much more applicability. And the unweighted version that we looked at is obtained as a special case. You obtain it as a very special case of the weighted situation. So whatever we did so far becomes a special case. In order to handle this, what you do is you sort of introduce auxiliary vectors of real numbers. Let the pair UV a cover for the given problem. See, the idea now is this is getting more complicated. Now you have the weighted graph, therefore these are weighted covers. These are real numbers, real vectors for the given problem, weighted problem. If Ui plus Vj the cost of the weight of the cover just sum all of them up. So let's prove the very first duality lemma. Let M be a perfect matching. Make sure you understand this clearly. All the while now I am looking at this complete bipartite graph. Okay, it's a complete bipartite graph in which I am looking at, so finding my perfect matching series is no problem at all. And UV a cover. Then weight of M with equality if and only if M is a maximum weight matching and UV a minimum cover. Proof. What's a perfect matching? Perfect matching actually amounts to saying that you have a permutation. Okay, M corresponds to alpha such that xi y alpha I then what is weight of M? That is the definition. That is definition. Yeah, it's defined that way. Okay. What is W of M? W of M is equal to sum I from 1 to n weight of xi y alpha I. Look at this. This is saying the inequality here is saying that this is Ui plus V alpha I. Which is equal to summation over Ui, I from 1 to n, plus summation over V alpha I from 1 to n. Alpha is a permutation. Alpha is a permutation. Therefore, this sum is nothing but V1 plus V2 plus V3 up to Vn. And that is, therefore, this is just C of UV. In case equality holds here, when would equality hold? Equality would hold means you have equality everywhere in each one of these summands. So this is equal to this. Ui plus V alpha I is equal to W. Okay? So in case of equality, okay? This is sort of theoretical basis for finding a maximum weight perfect matching in a weighted bipartite graph problem. Okay, this is the theoretical basis for doing it. Okay, what I would like you to do is go over the weighted bipartite graph matching problem in the book. Do you all have a book by West? Yeah, read that. Then we'll just quickly brush it up the next class. I don't expect you to solve problems based on weighted bipartite graph matching problem because it does need a computing device. Just cannot do it by hand calculation. Obviously, it cannot be done by hand calculation. Okay. So just see that what he is saying as algorithm is correct. And then we'll, so there is an algorithm exactly the same way as we have algorithm for the unweighted situation. And modulo that we are done with matchings completely. One can talk of matchings, essentially we stuck to matchings in bipartite graphs. One can talk of matchings in graphs in general. This is a more difficult problem. It's a much more difficult. So surprisingly, it is easier to talk of matchings in bipartite graphs than talking of matchings in general graphs. Take a simple graph which is not bipartite, but you can also talk of when that graph would have a perfect matching, etc. So this is like having a graph in general, even with odd cycles or whatever. In those situations, what you can do is take so S is a set of vertices. I look at G minus S. This will split into components. This will split into certain number of components. Okay? G minus S will have some components. Some of those will be even components. Some of those will have an even number of vertices. Those that have an even number of vertices, those can possibly be paired among each other. Those that have an odd number of vertices must use, suppose the number is 9 here, they would have to use at least one vertex from here. Therefore, clearly a necessary condition for a graph in general to have a matching, to have a perfect matching, is that number of odd components. By odd component I mean odd number of vertices in G minus S is less than or equal to the size of S itself for every S in V. What turns out to be true is this is also a sufficient condition. Quite a difficult proof. Okay, this is called Tutt's theorem, and this turns out to be also a sufficient condition to guarantee a perfect matching for graphs in general, not bipartite graphs. So we'll stop here for today. Weighted bipartite graph matching problem is something that read the material, and then next class I'll begin with connectedness. Okay. Thank you.